Thanks, all of you, for coming. It's almost like 6 p.m. It's a very busy day and a very late day for you all, I'm pretty sure. But thank you all for coming and showing your support for the community. Hey, I'm Arvind Bright, and I'm from the gRPC team at Google. And welcome to my first gRPC community meetup presentation. And today, what I wanted to talk to you all about was the new Kubernetes Gateway API. This talk is about the new gRPC resource, part of the Gateway APIs. This project is pretty close to my heart. This presentation is actually a very special milestone for gRPCRoute. This is because after 2 years of considerable effort from the team, and especially from Richard, gRPCRoute has finally been accepted by the Kubernetes Special Interest Group and graduated to V1. So we are excited for it to make its way into the hands of the community. So in this talk, we'll be covering the basics of gRPC and the Gateway API for people who are unfamiliar. We lay out a few great reasons to get started with gRPC today, and then we'll take a look at where gRPCRoute may be headed in the future. Now, what's gRPC? So the answer to this acronym would depend on whom you would be asking. So if you ask this guy, he'd probably say Golden Retriever's Pancake. So this is a cute little mascot. You could see that on our maintenance t-shirts. But for the rest of the world, the protocol acronym stands for gRPC Remote Procedure Call. And for those who are wondering what an RPC is, it stands for Remote Procedure Call. RPC is a way for one program to call another function that gets executed on another program. The call function might be executed in a different process on the same machine or on a different machine through the network. So gRPC is a modern, high-performance, cloud-native RPC framework. gRPC is general purpose, so which means it can be run on most flavors of open operating systems and also supports x86 and ARM architecture. gRPC can be run on servers, on a mobile device, in the browser, or in any embedded systems too. gRPC is language agnostic. This is a core essence of gRPC. So we have implementations in various languages like C, C++, Go, Java, Python, just to name a few. And gRPC is open source and is being accepted by the CNCF, the Cloud Native Computing Foundation, since 2017. gRPC also has a very special place in the Kubernetes ecosystem because of its base, because that's the basis of many Kubernetes' own APIs. For example, the container storage interface, the container networking interface, and the upcoming KNI or Kubernetes networking reimagined interface, all were based off, built on top of gRPC. Beyond the Kubernetes control plane, gRPC is used by thousands and thousands of engineering organizations to get their bytes where they're going and make sense of them on the other end. Now, gRPC has been built to power use cases to the last mile of computing. It relies on HTTP2 for its transport and uses protobuf as the interface definition language. This results in services where the APIs are well defined and the communication between the services are of low latency and high performance. So I spoke about the two components, the HTTP2 and protobuf. So HTTP2 started as a project called Speedy, whose motivation was faster web. So the performance gains can be put down to three major things. One, the requests and the responses are transmitted in binary format. The second thing is different requests and responses can be multiplexed on a single connection. And another thing is headers are compressed by default using HPAC. So protocol buffers. So protocol buffers or protobufs is an open source project for serializing structured data. You can think of it as being similar to XML or JSON, but smaller, faster, and simpler. Here are a few things that you can note down. So it's basically an IDL that allows developers to define the contract between the server and the client. It also supports tools to generate server and client stubs for multiple programming languages. And protobuf also ships the runtime libraries, which perform serialization and deserialization of messages. So basically, it's highly optimized for performance. Now, here is a sample proto file. I'm not getting into too much of details of protobuf, but then we can just glance over this because this will be more important in the later half of the presentation. So you can see that this is basically a text file, and this is the syntax that you would follow. And a protobuf message is the data payload being conveyed, and is structured as a series of name value pairs called fields. A protobuf service definition is a structured contract that specifies the methods a service provides and the message types it uses for communication. Cool. So for those of you who are from the REST or the JSON over HTTP world, let's call out a few key differences between gRPC and HTTP. The first big difference is that gRPC is schema'd. That means that you write your API definition first, rather than just being a documentation step. Your boilerplate client and server code then gets generated from that definition. gRPC uses protobuf for serialization and deserialization. This is fast, space efficient, and binary encoded. This is great for speed and efficiency, but it makes it a little more difficult to debug and send RPCs manually. I'll talk about that later, a bit more in detail later. Then there's the transport. So gRPC is built on top of HTTP2, which solves some of the blemishes of HTTP1. gRPC does things a little differently from browsers with HTTP2. Like browsers and REST clients use only HTTP2 with TLS. For plain text connections, which are useful for debugging or when running in a secure tunnel transport, browsers and HTTP clients generally only use HTTP1. But gRPC is all HTTP2 all the time. It's totally normal with gRPC to use HTTP to clear text without upgrading a connection from HTTP1. This also factors into the gateway APIs, which I will be covering in the later slides. And the final difference I'll highlight is gRPC streaming. So stream-based APIs provide a ton of benefits, including making it easier to build reactive applications, which seems to be the need of the hour. And streaming RPCs can last for hours or longer, but long-lived connections can also be a little more difficult to route. So even if you're not using streaming RPCs, the gRPC library keeps TCP connections along longer than most REST clients. This is actually to save on computation. Okay, so another thing that I wanted to give you all an overview about was the gateway APIs itself. So gateway APIs is actually the special interest group created for Kubernetes networking. The Gateway API is a Kubernetes project that started in 2019 that focuses on layer 4 or the transport layer and layer 7, which is the application layer routing for networking stacks. So these are actually APIs. So in terms of Kubernetes, APIs are normally resources, and these are APIs and require an implementation to be installed in the cluster. So these implementations should consume the APIs to implement the routing behavior defined in the API. It's a successor of Ingress API, which focuses on exposing a service inside a Kubernetes cluster to the outside world, basically north-south traffic. As the next generation of Ingress, the Gateway API has managed to make many improvements. It supports multiple protocols such as HTTP, TCP, UDP, and gRPC. It has strongly typed fields for traffic capabilities such as header transformations and traffic mirroring. It splits up ingress intent into multiple smaller resources. The gateway class is linked to an implementation controller and defines a common configuration for a set of gateways. So in terms of the Google Cloud platform would be providing the gateway class here. The gateway links to the gateway class and holds listener configuration and defines how external traffic can be accepted into the cluster. There are a collection of route resources defined for each protocol type, such as HTTP has HTTP route, gRPC has gRPC route, TCP route, UDP route, and TLS route. That links to the gateway, defining the defines routing, traffic shaping, allowing users to match on specific attributes within the traffic flow and route it to their service backends. Another thing to note is that these smaller resources can be mapped to roles within the organization. For example, the gateway resource can be used to expose a host name on a particular port and also specify TLS certificates needed for TLS termination and authentication. This is something only an app admin or a cluster operator should be able to configure. Similarly, only app developers have the knowledge to define routing and traffic shaping rules for traffic meant for their service backends. This split allows the organization to have isolation at resource level while sharing the same implementation infrastructure under the hood. Okay, so this brings us to the next topic, which is the gateway APIs basically are the future of networking within Kubernetes clusters. And the Gamma initiative, which is a short for Gateway API for Mesh Management and Administration, was created in 2022 within the Gateway API. So this basically focuses on using the Gateway APIs to also do east-west traffic management. The slide now shows one of the API semantics defined by the Gamma working group. There's a service producer, the server, and routes like HTTP route that can be defined for it. The route links to the producer's service using the parent ref field and defines specific traffic rules for traffic meant for this producer. Now, for any service consumer / client trying to reach this producer using the service's FQDN, the traffic will undergo any matching or transformation defined in that particular route. Okay. With this background, now it brings us to the main topic of this presentation, which is the gRPC route. The gRPC route API was introduced by Richard Belville from the gRPC team in August 2022. The API proposal, also called the GEP, highlighted the need for a dedicated API for routing gRPC traffic to a backend. The focus here is that gRPC routing over HTTP2 asset transport and protocol buffers as message format. The existing HTTP route could technically be used to route the gRPC traffic because under the hood we can still say it's HTTP to clear text, but the addition of new route type gRPC route significantly improves the user experience. So as you can see on the right, the proposal introduces support for method matches, allowing users to use gRPC specific constructs such as gRPC service and method for route matching. So this API has graduated to V1 and is released in the standard channel since version 1.1. It's great to see so many implementation already supporting gRPC route today. Conformance test for gRPC route has recently been added, and we are happy to share that they already pass on Contours, Cilium, and Envoy Gateway. With gRPC route graduated, we are hoping for more implementations to add support for it so more users can get access to it. In addition to these functional benefits, gRPC also provides with some great UX improvement for routing gRPC traffic. The biggest improvement in the current version of gRPC is the method matches. While gRPC uses HTTP2 URIs under the hood, users of gRPC shouldn't have to know or care about the way gRPC maps onto HTTP. Method matches let you route traffic for individual gRPC services and gRPC method without having to use these implementation details of the gRPC protocol. It's pretty common to route an entire gRPC service to the same backend. So if you omit the method field, the route that will route the whole service to that backend. It's somewhat less common, but you may have multiple services that have the same method names, for example, a V1 and a V2 version of the same service. In this case, you can omit the service name to route all RPCs with the same method name to the same backend. These are a few UX improvements we have I'm sorry. There are a few other UX improvements that we have planned as part of roadmap, and I'll be covering that in the later part of the presentation. Now, diving into the service mesh side of things. One of the most confusing things for folks using gRPC on Kubernetes is the long-lived connection aspect that I mentioned a while ago. When your client creates a new connection for each outgoing request, as with many HTTP clients, you'll go through full DNS and route flow for every request. But since gRPC keeps connections around for long as possible to improve performance, you only go through that process perhaps once over a course of an hour. Now, the most important way to route requests to a collection of service pods in Kubernetes is a service with a type cluster IP. So services with type cluster IP gets a virtual IP or a VIP. This is the single IP for that service, and when TCP connection is made to that IP, kubeproxy will balance the connections to one of the server pods associated with that service. When your client creates a new connection for outgoing requests, this will result in all your requests being balanced across all your server pods. So the request load and CPU utilization should be pretty uniform across all servers. For example, suppose you have 10 backends and 100 clients, each of them with the same request load. Then the request load across your backends might look something like this on the left side. You can see that HTTP gets relatively uniform distribution here, while on the right, gRPC is much less so. Why is this going on? This is the thing that I was talking about that the folks are usually confused about. So let's look at an example. Let's look at the example where the cluster IP is used with an HTTP route. So we've got a basic setup here. One HTTP client pod configured to send requests to a service named foo. So this client starts its request to foo. Now, the first thing it does is sends a DNS request for foo, gets a response back. So the virtual IP here is 10.0.1.1. The client will take that IP and establish a new TCP connection for the request. Now, Kubernetes will see the VIP is the destination of the VIP of the destination of the TCP connection and balance it to one of its backends. In this case, the client got connected to backend 1, and backend 1 returns the result of a request 1. So then the HTTP client sends a second request. It may or may not do another DNS request depending on caching, but will almost certainly initiate a new TCP connection. Kubernetes will ensure that the connection goes to a backend. In this case, 10.0.0.2, we've already seen a spread across different backends. And the third request, the same story, yet another new TCP connection, yet another chance at hitting a different backend. So we've recapped how HTTP traffic works in Kubernetes right now. So what happens in a gRPC client and what is the difference? So the initial thing looks the same. There's a DNS request. The client goes, asks for foo, and will get back a VIP, which is 10.0.1.1. The first request also looks the same. It is when we hit the second or the third request that we realize things are in the same way as with the HTTP client. gRPC keeps TCP connections around for quite a while because setting them and tearing them down is costly in terms of latency, CPU cost, and network congestion. But because gRPC keeps them around, the cluster IP routing mechanism just isn't super effective. As a result, you get pretty bad balancing. Coming back to this graph, this is really just the law of large numbers. So if you repeatedly roll a die, the chart showing how many times each phase has shown up is not going to look uniform until you hit a very large number of dice rolls. So in this example here, gRPC got 100 rolls because we really trying to establish a new TCP connection like after a big period of time, while the HTTP got 10,000. That's a big difference. And the difference clearly has implications for load distribution. But of course, I'm telling you this because gRPC makes it better. Because the ultimate solution to this problem is service mesh. Service mesh moves all of the routing logic directly within the client pod. And now you will start getting rock steady uniform load if that's what you want. And if you don't want that, you can configure the load balancing to happen exactly the way you want it to. In the past, when folks have reported this issue to the gRPC team, we have recommended service mesh to them. At the time, service mesh involved a lot of setup, like a lot of routing configuration. The routing configuration might actually have to be done outside the cluster and stuff like that. But now with gRPCRoute, setting a service mesh in Kubernetes has become easy enough that I no longer feel any hesitation in recommending that solution to this problem. It really is the simplest way to solve this issue. There are a couple of other more invasive solutions that do not require service mesh, but it's not covered as part of this presentation. Okay, so we've looked at a handful of reasons why you should start trying out gRPC today. But as soon as the idea of a gRPC route resource was brought up, the community was very eager and also suggested a bunch of features. And not all of them have made it in the first revision, but we have already touched on a few. The first is a feature that actually already somewhat real, gRPC web transcoding. This was sort of covered in our previous community meetup by you. I did see him there, yep. For those of you that aren't familiar, most browsers don't implement the full HTTP2 spec and therefore cannot support the gRPC protocol as it runs in data centers. As a result, there's a sibling protocol called gRPC web that lets you use the same developer flow as gRPC, but from the browser. Historically, you had to manually configure a proxy to do this transcoding, but several implementations of gRPCRoute, including Envoy Gateway, will take incoming gRPC web traffic and automatically transcode it to gRPC proper. These implementations are running ahead of the spec. There's actually nothing in here yet about gRPC web transcoding. The next step is to use what's out there in the wild as the basis for an extension to the gRPCRoute spec that includes gRPC web transcoding. Now, something that's very similar to gRPC web transcoding, that's HTTP plus JSON or REST transcoding. Very similar reasons for this as gRPC web. Some people just prefer using REST from the browser. These people put HTTP annotations in their proto definitions. These add extra information that allow proxy to map certain HTTP URIs and HTTP methods to gRPC RPCs. So REST in and gRPC out. In the example here, you can see we have mapped our echo RPC method to /v1/example/echo. So you should be able to hit the gateway with that URI and trigger gRPC RPC to the backend. At the moment, the most common way people do this is to generate proxy code from their proto, compile that in a binary, deploy the binary into their cluster and configure traffic through proxy. Exhausting, right? Well, the idea here is that we would be able to add a single Boolean knob to gRPC route that says, hey, give me REST in and gRPC out, and the rest should just work magically. Another key thing to call out is now there's reflection. For those of you who aren't familiar, protobuf is a binary on the wire. So it's very hard to craft gRPC requests because it's basically binary encoded. You need the type information in order to send a request to the server from the CLI or use a tool like Postman. You can do that by having the protobuf files on a file system, but that's a real pain. Instead, most people make use of reflection protocol. Reflection is a secondary service you run on your server that tells clients the type information for that particular server. With reflection server, tools like gRPC curl just works. Unfortunately for folks running gRPC servers on Kubernetes, this means that in addition to your application's standard RPC services, you will also have to route the reflection service to those servers. Basically, we want users to add a catch-all route rule for reflection. In the future, we'd like to extend gRPCRoute to automatically add routes for reflection, probably as an opt-in feature. So let's stay tuned for that. And last, but certainly not the least, there's payload routing. This would be a feature where you could route RPCs to different backend based on the content of your protobuf requests. This is actually where the main, the power of gRPC route comes in. This sort of thing isn't super standard with REST because in REST, the payload is human readable. So parsing JSON is actually quite very expensive. But with protobufs, checking the value of a single field is a relatively inexpensive operation. So routing this way isn't prohibitive. This sort of thing is done all the time in Google with the internal protocol that they use. You can imagine a payload matcher in addition to the method and header matchers that we currently have in gRPCRoute. So in this aspirational example, you see we're matching traffic for the login method only if it's particular user logged in. Of course, this will require type information, and so reflection will be required for this. There aren't any current open source data plane implementations for this, but little further out, there should be more that's coming in. Cool. That brings us to the last slide that I have and the end of my presentation. So the presentation is actually recorded, so it'll be shared to you all, and the doc will also be shared. So I think we'll open the round for questions.
Does anyone have questions or clarifications they'd like?
Yeah, are there any tables showing performance comparison versus JSON and REST and stuff? Table showing performance because you said it's better, right? So
right. So that again is very case to case, but then we have our benchmark results published on the website for every single language implementation as well. You can take a look at that. And we have had other presentations in our gRPC conf where people from outside have come and shown us the real world use case where they've actually migrated over from REST to gRPC and what the benefits are.
Thank you very much, Arvind.
Yeah, sure. Cool. Yeah, thank you.